All right, let's take a look at rational functions. So rational functions, you can see here with f of x in this first example, right? You got the division here of two polynomial functions. We've got a quadratic polynomial right here in the numerator, right? And we have another quadratic polynomial in the denominator. Now with these polynomials, we want to go ahead and factor, because on a rational function, right, when we have a fraction, we want to see if we can reduce by canceling out any common factors, and if we can simplify it. Well, as you notice, in this polynomial, we factor the quadratic, x squared minus 6x plus 5, which they've already done for us, produce the two linear factors of x minus 1 and x minus 5. Right, well, in the denominator, with x squared minus 8x plus 15, it's two linear factors of x minus 3 and x minus 5. Well, we notice we have a common factor of x minus 5 that divides out. So it does reduce. This function simplifies. All right, and we're going to talk about those characteristics here in a little bit. Now, as we're looking at sketching graphs of rationals, which is what we're doing here, we want to get a graph of this rational function, which they've produced already over here on the side. You can see its graph. But we want to talk about where this information comes from. Now, the key characteristics are asymptotes. Right? We have asymptotes, which are lines that shape our graph. So either horizontal lines or vertical lines, and we have even slanted lines we'll call oblique asymptotes. Now, we're going to focus on two types in our module, horizontal and vertical. So with a horizontal asymptote, right, we're looking at the degrees of our two polynomials. We'll always compare those. So we look back at the original functions. We had two degree 2 polynomials. So again, compare the degrees. That's going to be your first step. All right, step 1. So as we compare the degrees, degree of the numerator polynomial, right, is 2. So numerator degree equal 2, and denominator degree is 2. So again, they're equal. So numerator equal denominator degree. So whenever they're equal, all right, whenever the degrees are equal, all right, we're going to have a horizontal asymptote. Now, horizontal asymptote is an equation of a horizontal line. It shapes our graph. Our graph will flatten out at the location of this asymptote on the ends. Now, horizontal lines, again, are y equal to a constant. So as we look, we see our leading coefficients. Now, our leading coefficients are both 1, right? With both of these polynomials, we had x squared as leading terms. So it's the ratio of those leading coefficients. So 1 over 1, which is 1. So y equal 1 is where our horizontal asymptote occurs. And you can see that over here. So here's our graph, right, of y equal to 1. So you see again the graph as it goes to infinity, right, as it goes to negative infinity. What happens to the graph? It gets closer and closer and closer to this line. It's like a magnet pulls your graph to it and starting to flatten out in that location. So our horizontal asymptote is the equation of the horizontal line, y equal 1. Now this is not part of the graph. It only shapes it. So you can see we dashed in this horizontal line. Again, our graph is again approaching that line. It doesn't define points on that graph. So again, it's just again helping us shape it. So again, it's an imaginary line. Now let's go ahead and talk about the vertical asymptote, which is what I usually like to find first. So vertical asymptote, all right, is again the zeros of your denominator. All right. Well, we reduced our denominator. So remember now we had a common factor that divided out. Right. So with the look at wholes in a rational, wholes will occur whenever we have a common factor take place. So only if a common factor exists. So let's talk about the whole, and then we'll go to vertical. So with the whole, so we have a common factor of x minus 5. All right, so let's go ahead and write that down here. Again, this common factor here. Common factor is x minus 5. All right, well, the whole will be located at the 0 of the common factor. So what's the 0 of this common factor? when will x equal 0? So x minus 5 equals 0 when x equals 5. So we're going to have a hole at x equals 5. Now a hole is a point, an ordered pair, which our graph, right, will jump over. It's not part of the graph, it's a point of discontinuity. So let's find the ordered pair so we can use it to help graph our function. So what would y equal? All right, y, well, to find y, we just plug in our function. So let's go back to f of x. Now remember, we reduced it. So we're going to take out x and plug in 5. So that'll be 5 minus 1, right, as we take out x in the numerator. All right, in the denominator, we had x minus 3 in our reduced form, 5 minus 3. So we ended up with what? 4 over 2, which is 2. So y is equal to 2. So that means we have a hole at, what, 5, 2. And you can see that here. There's that hole. There's the hole in that graph. So yeah, our hole, we have 1. There's one common factor. And that common factor, again, is x minus 5, which produces 0. Or 5, which is the location of that hole. So again, 5, 2. Now with that, let's go back to the vertical asymptote. So the vertical asymptote will be the zeros of any of your remaining denominator factors. So we're going to look at the denominator of our polynomial. Here again, quadratic denominator. So in this rational function, right, we have a denominator factor of x minus 3. So when does x minus 3 equal 0? Well, when x equals 3. So we have a 0 of 3 there in the denominator. So with that said, we're going to have a vertical asymptote. A vertical asymptote at x equal to 3. So this is an imaginary vertical line. So remember, what are asymptotes? Again, equations of a line that shape our graph. So you can see here on our graph here to the side, what they draw in here at 3 on the x-axis. Right here at 3, we're drawing in this imaginary vertical line. And what's our graph to it? Getting closer and closer and closer to it. All right, now I won't ever touch that line. Let's say undefined value at 3. We know the denominator becomes 0 at that location. So again, that's the vertical asymptote. So x equal to 3. Of course, x-intercepts, we can easily find those in our function. You want to find the x-intercepts, right? You're going to find out when the function equals 0. Right, now in a rational function, right, we got a numerator polynomial and a denominator polynomial. When does it equal 0? Whenever the numerator equals 0. So as we're solving that for x, x-intercept should be at 1, right? We should have a x-intercept point of 1, 0, which we do. You can see it up here. There's that point of 1, 0. So yeah, there's our x-intercept. X-intercept would be at 1, 0. Right, now y-intercept, of course, how we find that algebraically. Right, y-intercept, we're going to let x equal 0. So we're going to evaluate our function with an input of 0. So that would be what? 0 minus 1 over 0 minus 3, which is negative 1 over negative 3, or 1/3. And right here is that point, 0, 1/3. So y-intercept would be at 0, 1/3. All right, so again, this is looking at these characteristics of a rational graph, right? Asymptotes, horizontal and verticals, equations of lines that shape our graph. Holes again, points of discontinuity, breaking our graph, an ordered pair in which our graph jumps over. And this one, of course, is at 5, 2. All right, again, shaping it. Now, the only thing we haven't answered, we like to always talk about, is the domain. Domain, all the real number values of x. So where's our graph take place on the x-axis? Well, everywhere except where we have a hole or a vertical asymptote. So x equal to 5 is an undefined value. We have a hole at 5 and at 3. Always. Domain, again, all the values of x that satisfy our function. 5 and 3 don't. 5 produces a hole, 3 produces a vertical asymptote. So as we're looking at domain, right, we're looking at what? All real numbers less than 3. So we'll put an interval notation. We see our graph taking place from negative infinity, right, to 3. I want to shade it in. And then, of course, from 3 to 5. And here, now remember, at 5, we have a hole. So we have a little break there. So we're looking at our interval. We put 3 to 5. And then what? What happens to the right of 5? All the way to infinity, we see our graph. So you can see we've got parentheses on 3 and 5, the two undefined values. But there's the domain of that graph. Again, you can see over here where our graph takes place on the x-axis. So that explains a little bit about rational graphs.